In 2016, I was looking to build my next thing. I'm a serial entrepreneur. I'm an industrial engineer. I had built a shopping app in the physical world, digital meets physical, that was acquired for $250 million. And I was looking to build my next thing. The logical next step would have been to do another consumer tech thing. But I really didn't want to. Instead, I made a decision to follow my heart and not my mind in terms of what I was going to do next. And that led me to Sam Gambier, one of the world's best cancer detection and treatment experts at Stanford, and an even better person. He was treating cancer patients every day in the clinic, and he had lost his only child to cancer at age 16, Milan. You can imagine what kind of energy he had to address cancer in new ways.
This brings me to Milan. What motivates me is knowing that if he had been born 100 years from now, the tools of precision health would have possibly allowed him to live much, much longer. I remain optimistic that the fundamental basic science that we all continue to do leads to new technologies that will help re-engineer our own bodies so that we can detect disease early. Welcome to the revolution.
3 months after Sam and I met, he shared something with me that I could never forget. It was an idea that was exactly on that intersection between the physical and the digital world that I love so much. And when I was thinking about this new world that I wasn't familiar with, I learned something about cancer, and it's probably in some ways obvious, but amazingly simple to say. What is the biggest problem? What's the #1 goal we have in treating cancer? It's to kill the bad cells, but not the good cells while you're doing it. And that simple statement belies how incredibly difficult this is. Why is it so difficult? Because cancer cells are your own cells in your own body. They are not a foreign invader like a virus. Your own cells have just slightly changed, mutated. And that's why they're really good at hiding. It's in fact so difficult that the guy, Siddhartha Mukherjee, who wrote one of the best books on cancer treatment ever written, won the Pulitzer Prize, writes in his foreword that malignant, meaning cancer, and benign are so genetically intertwined that unbraiding them is one of the hardest challenges faced by our species. And what does that lead to in practice? If you get chemotherapy, why does your hair fall out? Your hair doesn't have cancer. It falls out because the cells are dividing fast that make hair cells, that make hair. And so does the cancer. And the drug is designed to hit fast dividing cells. And we've made a lot of progress. Some of these drugs are getting more and more specific, but they're still not really there. We still have this problem of the drug is focused on something, but unfortunately that something is also on healthy cells, and it's called on-target, off-tumor effect. And what can we do when that happens? There's only one thing you can do. Lower the dose of the drug, because it's so toxic. And when you lower the dose of a drug, what happens to the efficacy of the drug? It doesn't work as well. And so Sam came and he said this to me. What if we could turn the whole table? What if we could make the drug inside the tumor by the actual cancer cell, where it's needed and nowhere else, nowhere else? Well, we see how bad this is still today We have lung cancer at 1.8 million deaths per year. And the 5-year survival rate has doubled in the last 20 years. It's wonderful. Unfortunately, it has doubled to 28%. That means 72% of diagnosed people with lung cancer will die in the next 5 years. So we have a long way to go. And we need new approaches. And if we could make the therapy where it matters, we would be in a different spot. The question is how? And Sam said this, what if we could make a switch, a genetic switch? So you inject it into the body, and it goes everywhere. It enters healthy cells randomly. It enters cancer cells randomly. But it only turns on in cancer cells. And when it does, it programs the cancer cell into a little factory that has to make its own drug against itself to activate the immune system, to attack and kill it. Does that sound like science fiction? That's what I thought. And then we went to work. I somehow couldn't forget the whole thing and couldn't get it out of my head. And we were trying to think about how to do this possibly and make it work. Because remember, it's so difficult to understand which is which, the bad and the good cell, remember? So then we said, okay, what about AI? This is, by the way, way before AI was really cool. And we said, what about AI? Could AI be more than really cool chatbots? Could AI actually extend somebody's life? Fast forward 8 years. Sam, a brilliant gene therapy expert, David Tsui, and I started a company called Earli. Earli, with an I. And then we said, we need to get going on this exact approach. And then in a deeply tragic twist of fate, Sam died from cancer. And 3 years later, his beloved wife, Aruna, died from cancer. The entire family is wiped out by this terrible disease. That gave us a lot of grief, and then massive determination to carry his torch and make this thing work. And this is where we are now. I would like to introduce to you a new genetic cancer switch at work. On the left side, you see a mouse, and it gets a construct, a compound, a drug, injected through the tail vein intravenously. And the compound goes everywhere in the body. You see how it goes everywhere? The green means it's everywhere, right? There's also a tumor in blue. So where would you like this switch to activate? In exactly one spot, correct? In the tumor. And here's where it activates. Everything in gray means it's not active. It's off. Everything in green or blue means it's on. And there's only one spot where it's on, and that's the tumor. And that took 8 years. To program these cancer cells to actually become a drug factory, we had to create 3 major innovations. Let me introduce you the first part. This is the actual construct, as you see here. The first part is a lipid nanoparticle. What is a lipid nanoparticle? It's basically an encapsulation. Think of it as a delivery truck. It can take DNA cargo and bring it to a specific part in the body. You all know lipid nanoparticles, even if you've never heard of it, because you probably had it in your body with the COVID vaccine. The problem with these lipid nanoparticles is they all go into the liver. The liver flushes out everything that doesn't belong in your body. Alcohol, lipid nanoparticles, everything is gone after a few minutes, hopefully. So how did we hide this? We had to stealthify that thing so the immune system wouldn't see it. And it could circulate longer in the body and had a chance to go by the tumor and actually reach it in the lung, for example. So once we had done that, We needed that genetic switch that only turns on in cancer cells. I'm going to get back to this. And then there's the third part, which is once it's in the cancer cells and it has turned on, you have to program the cancer cell to make a drug against itself, correct? It has to become a factory. And it activates the immune system against itself. Now, about that genetic switch, these genetic switches are really complicated. If you take a piece of DNA as an instruction set, if you have only 10 variable components and 50 options, you get to possible number of combinations of 10 to the power of 17. And that is the number of stars in 500,000 Milky Way galaxies. Now, okay, what do you do now? How do you select which switches are actually relevant for cancer to turn on and off? So that's where machine learning and AI came into play. We went through thousands of human cancer samples. We analyzed them, sequenced them, looked at them, and went to machine learning in order to understand a pattern. And we finally found a pattern that turns on in cancer cells but not in healthy cells or benign tumors. And we also had to verify that in the wet lab, where you use the pipettes. In the wet lab, usually you can do 50 things in 1 week. We needed to hundreds of thousands. So we hired a specialist, brought him on board. Now we're able to look at bar-coded sequences you can read out at 250,000 a batch. That allowed us to look at a lot of stuff. And the answer was a completely synthetic switch that nature has very little to do with now. It wouldn't exist without machine learning. In fact, we tried and we failed. Initially, we tried without. It didn't work at all. And here is how you see how it failed. It produced only 26% responses. These are each individual lung cancer sample results. And with the new one, 95% on the same samples. Now, if you think about the future now, large language models, chatbots, what are they doing? They're taking text and they predict the next one. Now, what is DNA? DNA is text. It's 4 letters. The alphabet of DNA has 4 letters that keep permutating. So now we're using large language models to go for the next part and predict the next one and actually then analyze which one was likely going to win. And then we verify that in the wet lab on actual cells. And then we put it in mice to double check it. And so with every loop, this thing gets better. And some of you might have heard of AlphaFold, which was using artificial intelligence for protein design. We're doing the same for DNA design. Now, all of this would be useless in an intellectual exercise if it didn't actually kill tumors. So this is probably the most important slide for you. Here you see the exponential tumor growth in a mouse with no treatment in black. Our construct in red with no payload, meaning payload means no drug produced. And in green, when the cancer makes its own drug against itself, in this case, a cytokine, IL-12, which is like a messenger to the immune system to attack and kill. If you injected that into the body without our switch, the mouse would die because it's too toxic. So it's only useful to do this if it's not elsewhere in the body. Remember that? Here it is. Lots in the tumor, nothing in the blood serum. And how does this compare? If you look at what the world has been doing, these are the best players in the market. This is how much is in the blood for them. And the lower the bar, the better. And this is where we are now. We're at 1,500 times lower than the best player in the market. Now, this is, I'm sorry to show you this, but this is how lungs look of mice that have tumor burden, and it's so much burden that you can hardly see the lung. And this is how it looks when the cancer makes its own therapy against itself. It's almost clean. This also is safe in large animals. We tested this in monkeys. So now it's high time to get it to humans, right? So next summer, we want to dose the first human being with this. And from there, there are so many opportunities from here. Imagine you could not just do lung cancer. You could do different cancers, ovarian, liver, bladder. You could go to different types of drugs. You could go to different patients groups. You can even go, potentially, we haven't done this yet, to autoimmune diseases. Because if you can locally upregulate the immune system, could you also locally downregulate it? So we will try that. So in summary, this is very specific to cancer. It activates across many patients. It's not only in the liver, and it only activates in cancer cells to make them into factories that make their drug against themselves. So, now, we don't know if this will work in humans. I believe it will. But if it does, it will start a new paradigm of AI meeting human insight, meeting real-world biological data. And that leads to a virtuous loop that gets better with every round. And the ultimate goal here is to turn biology into programmable biology against diseases. So, wish us luck. It's for everyone. It's for all of us. But I'd like to think that from somewhere, Sam is watching and is smiling. Thank you.